Okay, welcome back everyone to another lecture. Today we have a very special lecture. I'll make a couple of introductory remarks and then I'll hand it over to our guest speaker who I'll introduce as well. So let's go through a couple of housekeeping notes. We are, in terms of topics, covering visualizing CNN today. Okay, and so finally, let me now introduce our speaker today. We have our guest speaker is Dr. Ram Salvaraju. So Ram is a senior research scientist at Salesforce Research. He got his PhD at Georgia Tech with Devi Parikh, who's a faculty member in the School of Interactive Computing. Ram actually has done a lot of interesting work. One of the reasons why we are always happy to have him come back, and he's given this lecture last year, and why we're happy to have him come back and give this lecture is he is, to put it not so humbly, one of the world's leading experts on this topic. Ram's PhD thesis, one of the core things that he developed in his PhD thesis was a technique that is now taught in classes. And not just my class, but other universities as well. So you are going to be implementing a method in this homework that is called GradCam. Ram developed that method in his PhD thesis, at the beginning of PhD thesis, and then he went on to do other follow-on work after that. That one paper has been cited more than 2,500 times. It's a loose proxy for how valuable people have found that work to be. It is, of course, a noisy metric, but it is a metric. By all quantitative metrics, Ram's one piece of work is the most impactful work that any of his co-authors have ever done. So GradCam is my most cited paper. It is Devi's most cited paper. It is anybody who was on that paper, that's their most cited paper, and it's really all large credits to Ram, his PhD thesis. This method is also now implemented as default on visualization libraries for PyTorch, so Captum, visualization libraries for TensorFlow in Keras. It just comes implemented out of the box, and while there have been a number of studies over and over again that saliency-based methods can often be fooled and can fool experimentalists into interpreting something more than there is, GradCam has over the years fared quite well in those comparisons. And it's one of those things where, excuse me, one of the reasons why it is so popular is it just works. It does interesting things. So with that introduction, I will not take too much of the time and hand it over to Ram to cover this lecture. Go ahead, Ram.
Thanks for the wonderful introduction, Dhruv. I do think that you gave me a lot more credit than I deserve. Thank you so much for your wonderful guidance and Devi's wonderful guidance during my PhD. I attribute everything to that. With that, so the quest today is largely going to be about understanding what a trained convolutional neural network is learned. We'll be looking into getting intuitions as to how CNNs work, what techniques we have to analyze the internals of the network, and there's going to be a lot of pretty pictures today, so stay tuned. All right, so here's what we are going to cover today. In the first line of work, we're going to cover what do individual neurons look at in images, and how do every pixel in the input image affects model decisions, and do CNNs actually look at the same regions as humans do while making decisions. And the next question we're going to look at is if we can synthesize images to see what the networks are actually looking for. All the things that we discussed today, you can use to delve deeper into your network to debug them. For example, you can understand if, say, a 5x5 filter is better than a 7x7, and so on and so forth. Yeah, the first question. So what do individual neurons look for in images? Yeah. So what's really going on inside a neural network, right? What do they do? what are they looking for? So far, we have kind of seen a convolutional neural network as a bit of a black box, right? So you have an input, you have a convolutional for convolutional layer, and then you have a relay on top of it, followed by some pooling layers, and then a bunch of these concatenated, and finally you have, say, a couple of fully connected layers that give you a score for a particular class. These class scores are interpretable, right? So, but the question here that we're asking is, what are these other intermediate middle layers doing? What kind of things are they looking for? What kind of things in the input image are they looking for? Right? So visualizing the first layer is relatively simple, right? This is the layer that directly attaches the image, is the first layer that it attaches to the image is a convolutional layer. So in case of AlexNet, the first layer has about 64 convolutional filters, and each filter is 11 by 11 by 3, because you have 3 channels, R, G, and B. And then these filters get placed over the input image, where you take a weighted sum, basically a dot product, and then slide it at different locations in the image. The first layer in a product is directly taken with the input, so we can literally just visualize the weights of the convolution layer to see what they're looking for. And one thing to note is that when taking a dot product with any vector, the vector that gives the maximum dot product under some norm constraint is the vector itself. And that's exactly why we can visualize these weights as images that we see on the left here. So, for AlexNet, you have 64 features here, and each one is 3 by 3. It's 11 by 11 by 3. And then what we can see here is a lot of them are looking for oriented edges and different angles and positions. The interesting thing is that this network is only trained on natural images. So it's the same kind of patterns that emerges even across different kind of architectures that you can see here. And interestingly, the human visual system is also known to detect these kind of things, like oriented edges at very early layers in the human visual system. And it turns out that the neural networks, these artificial neural networks also learn somewhat similar things. But now can we do the same thing for intermediate layers? It turns out we can, but a lot of these are not interpretable for humans. The reason is the second convolutional layer receives a 16-channel input, because the output dimension for that first layer is 16. So now this layer does some, say, 7 by 7 convolutions with, say, 20 neurons. The problem is that we cannot visualize these 16-dimensional images. So what we can do is just roll it as 16 7 by 7 grayscale image, and we'll have 20 of them. They seem to be, here we can see that they seem to be looking at some kind of special structures, but there's nothing meaningful here. So what this gives us is the kind of activation patterns that maximally activates the second layer neurons. But yeah, we don't need to come up with more fancier techniques to understand them. So now, yes, the weights on the intermediate layers are not interpretable, but the activations are somewhat interpretable in some cases. So let's look at that. Here's a visualization that's been put together by Jason Yosinski. This is a very popular paper. And this visualization got really popular. So here in this visualization, what you can see is for different layers, you can visualize the activation maps when you feed an input. The input is shown on the top left, and you have the bunch of layers that are shown here. And for example, right now we have highlighted the convolutional 5 filter, and we are visualizing this particular neuron. I think it's neuron number 26. And you can see that this is where this neuron looks at. And it does seem like this neuron is particularly looking to, it gets activated when it sees a wheel. Yeah. And remember that there's 5 layers of AlexNet. You have 128 of them, and each one is 13 by 13. And so we have 128 of these visualized here. And each one of that is 13 by 13 dimensional. and we are actually enlarging it to the image size here to visualize what they're looking at. Yeah. So now, in the previous case, we've been looking at visualizing the filters, which are the weights of the network. But here, let's look at the intermediate activations instead. Here we are basically visualizing what type of patches from the input image cause a maximal activation of different neurons. Let's say we pick a particular layer, conf5, and choose a particular neuron, say neuron 17. So what we can do is feed forward many images and see the images that activate any particular neuron. Then what we can do is visualize the patches from this large data set of images corresponding to the maximal activations of that particular feature in that particular layer. And then we can sort these patches and the activations in the particular layer. And here, these are some of the examples that you see for one of the neurons in conf5 layer. You can see that it seems to look at the human faces, and that's this particular neuron on the top. And this particular neuron seems to look at different kinds of flowers. And then this particular neuron seems to look for shiny objects. And then there's this neuron that seems to highlight the written text in images. So now we looked at intermediate layers. Let's go to the last layer. For most of the classification tasks, it's common to have a fully connected layer at the end. Considering how less interpretable a 16-dimensional weight of the second layer is, now imagine how difficult it is going to be to visualize this 4096 dimensional weights in the final layer. And so similarly, like what we did before, we can try and feed in a data set of images to a trained CNN and record the 4096 dimensional vector corresponding to each of those images. So let's just do that. Before that, let's consider a baseline where we are literally taking images and feeding in a bunch of, and then just computing a k-nearest neighbor to each of those images. Here you can see that, for example, the second image here is a picture of a dog. Here, in fact, all the images, like a couple of them are dogs, but you can mainly see that it's looking for some white blobby structure. So all the directly taking nearest neighbors in the pixel space does not seem to be very interpretable, right? Now let's look at the 4096 dimensional vector, and here you have a test image here, and you record the activations for several of the input training images that are fed to a CNN. And then for the one that is closest match, you display that image here. So for example, you can see that for this particular image of a flower, you can see most of the nearest neighbors seem to be flowers, similar looking flowers. An interesting example, another one here is an image of an elephant, and it's facing the right. But here you can see that it actually, in the third image here that is returned here is an image that is actually facing left. So what you can see here is that the kind of invariances these networks have learned. In the pixel space, these images might be very different, but in the 4096 dimensional feature vector space, you are getting very similar representations. So yeah, that's interesting. Let me see if there are any questions here. All right, no.
Yeah, they've been answered. The questions have been answered.
Oh, I see. Sounds good.
Ram, can I just make a quick comment? Would you mind going back to the previous slide? Yeah.
Yeah. This one?
So thank you. I want people to particularly notice the last row in Ram's slide, where there is a dog facing right and a dog facing left, and even the colors of the patches are similar but slightly off in the shade. And this would never happen, that the one nearest neighbor is the exact flip of the pose, would never happen if you did pixel distances, because pixel distances are highly sensitive to alignment. And this is telling us that your neural network in the embedding space of the last layer of activations, does not care about pose. And that's the point that Ram was trying to make. Now, if your problem is an image classification problem, losing pose information is a good thing, because all you want to answer is the category present in the image or not? But if your problem is, let's say, human body pose estimation or joint localization or other things where pose is really important, then this would be a bad thing. Presumably, this would not happen because your loss function that happens after this layer would penalize for losing pose information. And so what we are looking at is an emergent property where this neural network decides that in order to optimize my downstream loss, which is just classification cross entropy, I do not need to consider pose, because this objects with different pose are all annotated with the same category. And so this is a consequence of an emergent property of a representation. Go ahead, Ram. Thank you.
Thanks, Dhruv. Yeah, that makes a lot of sense. Yeah, and another thing that we can do, like we said, this is a 4096 dimensional space that is hard to visualize. We can do some kind of a dimensionality reduction technique to reduce it to, say, 2 dimensions that we can directly visualize in 2D. One popular technique is T-SNE, a T-distributed stochastic neighbor embeddings. Here's an example of what T-SNE can do. Here we are visualizing 28 by 28 MNIST digits. It's a data set of grayscale MNIST images. And we feed it through a convolutional network and extract the final embeddings, which are 4096 dimensional. And then we compress them to 2 using T-SNE. Here we can see that natural clusters are being formed where each cluster contains mostly a digit. Similarly, we can apply T-SNE reduction technique to the features from the last layer of a trained ImageNet classifier. To be more concrete here, what we are doing is we're taking large sets of images and getting the 4096 dimensional vectors, reducing the dimensionality at each location in the grid to 2, and then the closest one we are visualizing the original image here. So here in this particular thing, you can see that there are initially here you see a bunch of these flower-like objects. Here towards this end we see a lot of aeroplanes and so on. So here you can see this is a much more denser visualization. The high resolution visualization can be found here. The zoomed in version is on the left. Here, so yeah, like I said, this space, it seems like we can explore, this is a very high dimensional space, but we're able to run through this higher dimensional space, but we do seem to find semantically closer objects, semantically closer images to be closer in this higher dimensional space as well. So that's interesting here. Yeah. So the next question that we're going to look is, until now we didn't take into account the final decision, but let's look at how individual pixels affect the final decision that these deep networks make. The question here we're asking is, where does an intelligent system look to make its predictions? A cool experiment that we can do comes from Steeler and Fergus's 2014 ECCV paper, where this is an occlusion experiment. So what we want to do is to figure out what parts of the input image cause the network to make its classification decision. So what we'll do is to take our input image, in this case it's an elephant, and we then block out some part of that. So by blocking out, what I mean is that we take, say, we take a gray patch. It's basically, you take the average pixel value for all images in your data set, and then place it in any part of the image, let's say at the top left, and then see how the probability of the elephant actually changes here. And the reason why we are placing a gray patch and not a black one here is because one typical step that people that researchers do when training networks is to center them to zero. So every image you normalize it and shift it. So essentially, this gray patch would actually look like a black patch to an image to the network. And here, for example, when we place a gray patch at this particular region in the image, the probability of elephant does not seem to change much. But here, if I place it right at the face of the elephant, the probability drops. So we can get some kind of heat map visualizing how the probability changes as I move this particular gray region. And we can see that in the top, it does seem to look at basically the face of the elephant seems to, be way more important than other irrelevant regions. But here's an image on the bottom right. Here, the category is like a car wheel, but it does seem to not look at the wheel much. Like it does. One thing I want to point out that the visualization is actually inverted here. Here, the blue means that the probability actually drops significantly, and the red means it does not drop. And so, in this visualization, the problem here is that in order to predict a car, it does not seem to look at the wheel. And so we expected that the wheel would be one of the deciding factors, but the network seems to have learned a lot of redundant features. And yeah, so this approach is definitely faithful because we are clearly getting to see what kind of pixels change probabilities of the classes that we care about. But it's also very expensive and in some cases very heuristic, right? Because it's expensive because you have to place this gray pixel at each part of the image. And then, if your image is, let's say, 224 by 224, you need to do about 1 million forward passes to get this. So we'll be looking at much more faster ways to do this. Let's take,
yeah. Can you go back a slide? So there was just there was a question from someone asking how we can get this heat map. And so I wanted to just summarize that algorithm that Ram described. So the heat map is computed by first just once forward propping the original image, getting what your classifier is predicting for it and the associated score. So on the image on the right, the classifier is predicting African elephant and maybe an associated score of some probability from the softmax layer. And then you place a gray patch, which is really, as Ram explained, a zero set of pixels, a patch of 0 pixels in the zero-centered image. And you place that patch, the same sort of for loops as you would do for a convolution, and you're blocking certain pixels at where that patch is located. You forward prop again with these blocked pixels. You measure the probability of the class, and then you look at that diff, and you store that diff in the index of this 2D array, this 2D heat map. And the index is computed by the patch location. So the heat map is really just telling you, if I were to place a patch at this location, how much would my output probability change? And that's what that heat map is telling us. And so that's the answer to the question. One comment I wanted to make on this slide is that let's realize that these data sets have no part level annotations. There are just object level annotations, and there are not even bounding box annotations. You just get told somewhere in this image is an elephant, somewhere in this image is a car wheel. And then we just train pixels to class probabilities. And so when you then analyze what your network has learned and realize that it is sensitive to pixels that lie on the head of this object, of the elephant, that is an interesting phenomena. That is an emergent, interesting phenomena that by looking at multiple pictures of elephants, it figured out that there was some common part, and that common part happened to just be the head of the elephant. The network does not have any quote unquote understanding that that's the head. It has no annotation of the head, but it is sensitive to drops or occlusions of the head. And that's what it's quote unquote looking at. to make its prediction. Notice I say quote unquote because these are post hoc rationalizations that we are making to each other. We are providing those semantics, but we are just trying to understand what the network is sensitive to and what is not. And this is where the bottom example that Ram showed is particularly illustrative, where these are powerful models, but they can be sensitive to irrelevant features in your data, and therefore we have to be careful about biases in our data sets. If all car wheel images have text on the car body in them, the network will figure out that, or machine learning models will figure out that it is text that is predictive of car wheels, and what you end up learning are text classifiers, not car wheel classifiers. And you can imagine replace car wheel and text with much more serious examples like predicting whether someone should get a loan and race features or zip code features, and you get very tricky problems that we may actually be picking up on features that we do not want to. They just happen to be correlated in our data set. Okay, back to you now.
Thanks, Dhruv. Like we discussed, like computing an occlusion map is super expensive. Let's make an assumption here. And let's say our model is actually linear, right? So you have a W, X, there's a bias, gives you a score for this input image X. If that were the case, like for example here, you have the weights and you have an input here. What would you think is the importance of a particular dimension of the input here? For example here, we would say that this fourth dimension is 5 times more important than the first dimension here. And in fact, the last one actually says that the existence of the last dimension would indicate it would actually play a negative role in this particular score. So that way, this weight can be thought of as how important a particular feature is for a particular decision that the model makes. But our network is not. Definitely, we have a bunch of these ReLUs and max pooling layers that make our network not linear. But we can make it linear. At least we can have this assumption using Taylor series, where you can linearize this network. And once you do this, like if you linearize the network this way, these weights would essentially be the gradient of the score for the particular class that you care about with respect to these input pixels, right? So in order to compute this, we're just simply doing a backprop, which we typically do until we typically use backprop gradient descent to update the parameters of the network. But here we are not updating anything. We're just going one step further and visualizing the gradients on the input. In fact, here we would be updating these gradients when we are training networks, but we'll be going one step further to get the gradients to this input layer. So this technique was suggested by Karen Simonian, I think in 2014. So here it's just computing the gradient of the predicted class score with respect to the pixels of the input image. And this will directly tell us, like in a first approximation sense, for each input, for each pixel in the image, if we wiggle that pixel a little bit, by how much would the classification score change for that particular class. People have used this to get these kind of saliency maps. And there was this very popular algorithm called GrabCut, and which requires some kind of an annotation as to like where the object would occur. But if you use this kind of saliency maps to perform, to use for GrabCut, you'll be able to get semantic segmentation without any direct label data. So in this, they're using this GrabCut segmentation algorithm, and you see these really nice looking visualizations.
Ram,
Yeah.
can you just go back? Yeah, so I just want to make sure that this point was clear. So the second column in this figure, this is the saliency visualization, and this is what you are computing in your homework. We are looking at a white and black visualization because we are plotting the gradient of the log probability or probability or softmax. We can take any of them, but it is the, let's say, the log probability of the class that the model is currently predicting, and you are taking that gradient with respect to the pixels. So it's a gradient of or the partial of a scalar with respect to each pixel, and that's why we can visualize it as a 2D matrix. And we are reporting the intensity of that. Sometimes you'll see it rounded, sometimes you see it not rounded, but that's what that second column visualization is. And so the higher the gradient magnitude at any particular pixel, what that indicates is that the log probability for the class that the model is currently predicting is very sensitive to what that pixel value is. And so if it's sensitive to a pixel value, epsilon perturbations in the change of that pixel intensity are telling you that the model cares or is looking at that pixel. Yeah.
Just to illustrate what Dhruv, I think, is mentioning here, if you see if you're trying to compute the gradient, let's say, assume that this is your final classification score. Here, and for each pixel, you're computing this gradient, right? Like partial of the score with respect to this particular pixel, and then you just put these values here, and this will result in visualizations like this. Yeah. Oops. Yeah. Now, we would have learned about ReLUs, right? So here, but what about the backward pass of a ReLU? And I will quickly discuss like why we are talking about this. In the earlier case, we were just simply backpropagating the gradients all the way, following the actual backprop, the chain rule. But here, for example, when one thing to note is that when you backpropagate gradients through a ReLU, you take into account whether the forward pass activations corresponding to that particular dimension is positive or not. If it is positive, then you feed the gradients as it is. If the forward pass activations are negative, you don't pass that gradient, right? For example, here, this is what I mean. Like this is your ReLU. Here, when this input passes through a ReLU, here you would see that these values highlighted in red would be zeroed out. Now, let's assume that the gradients that you get from the higher layers is this. So you can see that the yellow ones are actually negative. When we backpropagate this to this layer, through the ReLU layer, you can see that it's not the negative gradients that are getting zeroed out. It's the regions where the forward activation was positive. These values are actually being zeroed out. And this is your regular backprop through a ReLU. Now, there's been another work, Beacons, and I think Dhruv will be discussing this in the future lecture. Here, what they do is they change how the backward pass works for the ReLU layer as just don't care about the forward activations, only backpropagate the gradients when they are positive. So, for example, here these values were negative, and these are getting zeroed out. Only the positive gradients are being backpropagated. So there's another paper that came out was guided backpropagation, which said that like zero both, like basically follow what the regular backprop for ReLU says, and also use this decon backprop to remove the negative gradients to flow back. And what they found is that, like, for example, in the earlier case, we found that doing a simple backprop actually resulted in like somewhat noisy looking images. When we do guided backdrop, like we talked earlier, it does seem to look at like much more crisper visualizations. But this does have a disadvantage in the sense that when you do guided backdrop for the category cat, it looks somewhat at the cat and the dog. And if you do guided backdrop for dog, it again looks at both dog and cat regions. Even though the network is understood or figured out that this, like where what a dog is and what a cat is, because it's a trained network, our visualization is not showing that the network has learned this. So in a way, these visualizations are not class discriminative. So that's where, that was
Actually,
our,
would you mind going back 2 slides? I just want to make a couple of quick notes.
this one?
No, the one before this.
This one?
Yeah, so I just want to make a quick note for people. The top row is just forward pass in a ReLU. There's nothing that we are introducing. The second row is just a visualization of backward pass or the chain rule, Jacobian multiplication as implemented for a ReLU, right? You just look at the thresholding happening at HL greater than 0 is just the Jacobian for this layer, and the multiplication by the gradient is just the implementation of chain rule. So there's nothing too fancy there. The bottom 2 rows that you don't actually look at the thresholding just on the incoming activation, but you look at the thresholding on the gradient, and the absolute bottom row guided backdrop, you do thresholding on both. The absolute bottom row in particular does not have any formal justification. Why do we do this? The answer is it leads to cleaner visualizations. There is no formal justification for the bottom row. There is an interpretation and a justification for the third row, which is called deconvnet. We will talk about that formal justification in the next lecture, but as far as you are concerned for this lecture, you don't need to understand that formal interpretation to know that it is just an alternate way of creating visualizations. We were computing gradients of the log probability of a particular class at pixels. Now we're just going to make a slight modification just at the ReLU layers, that we are going to, instead of doing regular backpropagation, we're just going to do this modified backpropagation, but still get gradients of loss with respect to pixels. And turns out that if you do the third row or the fourth row, it will lead to cleaner visualization. That's it. The third row in particular, we will talk about in detail next time. Go ahead, Ram.
Yeah. So that was a motivation for GradCam, right? Like, so you initially had these visualizations that seem to be very crisp, but they don't highlight what the network seems to actually learn, right? So the main motivation for GradCam has been that perturbing the semantic neurons in the image, and can we see how that affects the decision instead? For example, we have seen that earlier works which have showed that earlier layers capture low-level details like edges, blobs, but the later layers captured much more higher-level details like faces, objects, or parts of objects. So, and hence, the last convolutional layer seems to be the best compromise between higher-level semantics and somewhat detailed spatial resolution. We'll get to the algorithm here. So given an image like this, we feed it through the convolutional layers of a CNN. So the outputs of which can be, say, used for any particular task. Let's take the case of image classification, where you have a couple of fully connected layers followed by a final softmax that predicts, let's say, a tiger, cat in this image. Now we are asking the question, what are the most important neurons in the last convolutional layer that are responsible for predicting tiger, cat? So here what we are doing is we are doing a simple backward pass until the last convolutional layer. So we're literally just like, like considering this this part of the network here to be linear, and we are computing the gradients. And these gradients are going to be the exact same dimension as the input feature maps. And these gradients are class dependent because for implementation you're going to be one hot encoding the class that you care about, and then backpropagating, feeding that as a gradient and backpropagating all the way till the last convolutional layer. So this is going to be the same dimension as the feature activation, forward feature activation maps. Here we do a global average pooling on this. So essentially, you make this particular slice. You global average pool. You average that into getting a scalar, and you do that for each of these convolutional maps. So if there are 512 convolutional neurons in that particular layer, you'll have 512 dimensional feature importance, neuron importance vector here. And because we are trying to explain this particular image, we combine this with the forward activations, and then you do a weighted sum. So basically the weights are coming from these global average pooled gradients, and then we remove the negative values through a ReLU, and then this is the visualization that you'll get. Here again, this will be the same dimension as the last convolutional layer. For example, this is a visualization for VGG. The dimension is 14 by 14, but here we have expanded it to the image size. So here, this is GradCam. Now, here you can see that it for the particular class of tiger cat, it seems to highlight the regions of the cat. So that's interesting. We can do this for any task here, right? Like, so all we are doing here is computing gradients with respect to the output that we care about. So the only condition that is needed here is for the network to be differentiable. And that's the case for almost all the networks that we train, because we are anyway computing gradients, right? So for example, here, you can have an RNN or an LSTM that predicts a caption cat laying on the ground. This is an example of image captioning, the GradCam applied for image captioning, but you can have additional input channels as well. Here, for the question, is there a cat? For the answer, yes, we are visualizing where the model would look at. There's been this earlier work that we talked about, right? Guided backprop. Guided backprop, we saw that it gives you visualizations like these. But we can combine guided backdrop with GradCam through a very simple, just pixel-wise product. It's going to give you a visualization like this. So here you can see that for the particular class of tiger cat, it does seem to highlight that, say, it looks more at the stripes because it's that particular variety of the cat that we are asking the model to visualize. Not only this, just because the model predicted tiger cat, we're able to visualize this. We can also change and ask the question, where would you look at if you were to answer that this model has a dog category? So that's this. Here, we are changing the class to something that, let's say, the model did not predict. And we are following the exact same procedure here. And right now, it seems to look more at the face of the dog.
So just actually, can you go back? So just a couple of comments. So first of all, this notion that you can produce visualizations for any class, not just the one that the model predicts, is a really powerful notion. This is a notion of something called counterfactuals. Counterfactuals are, how else could the world may have evolved? What would I have done were the facts on the ground different? And so here, if the model had predicted a different category, what pixels would have been important for that for that prediction is the question that Ram's answering by changing the category for which he's creating the visualization. And Ram, can you go back one slide on like the core GradCam idea?
This one?
No, one more before you introduce guided GradCam. Yeah, so just for GradCam for classification. Yeah.
Oh, sorry. I come across.
Just that, yeah.
Right.
Yeah. So this is the core idea, and you can have the equation come up on the slide, Ram. This is the core idea, right? The fact that this can be applied to any task-specific network is just a generalization of the idea. The fact that GradCam can be combined with guided backprop is just bells and whistles, but this is the core of the idea. And to be perfectly honest and tell people a realistic story, the first time Ram came to Devi and I, and he was describing this idea, we were listening to him. Wait, you do backprop, usual backprop all the way till convolutional layers, and then you do some global average pooling, and then you combine it with weights that are global average pooling of activations. And we were both like, why? This makes no sense. How did you even think of trying this? And it's a weird idea. It was a creative idea. It was different from what people were doing. We then, for the paper, sat down, and to be honest, we engaged in an exercise which was empirical first. Ram had clear, convincing evidence that it does something interesting. Here is an operation that appears to do something interesting. We sat down and we provided an explanation in our paper to the best of our abilities. We said this is a partial linearization of the network that is downstream from you. And we, to be honest, came up with explanations that were post hoc rationalization. But this is a fascinating journey that idea works. It works for many different problems. It works across tasks. People have replicated it. And as you all engage with this in your homework, I encourage you to think about what may be the limitations, what is it lacking, how might you change it, why does this work, why do you get those visualizations? And if you have thoughts and suggestions and ideas, reach out to Ram offline. This is one of the reasons why we are inviting guest lecturers, so that you can form connections even beyond this. Okay, back to you, Ram.
Thanks, Dhruv. Some of the interesting findings that we had with GradCam, like that even non-attention-based simple CNN LSTM models seem to look at appropriate regions. For example, here, this is one of the first neural network-based captioning models that predicted a group of people flying kites on a beach. Like previously, there was no way to visualize where the network was looking at, but here we seem to see that the model seems to be looking at these kite-like features along with some people on the beach. Here, a man sitting at a table with a pizza. Here, it seems to be looking at the man and a little bit at the pizza. But here you can see that the caption though says the man is sitting at a table with a pizza, but the visualization does not seem to highlight the table. So this somewhat indicates that the model might be just hallucinating the table. Basically, the language model is actually maybe taking over and saying, a man is sitting, so of course it has to be sitting at a table if there is pizza. So that kind of thing, you can see that we'll be able to visualize these approaches. For example, here is GradCam applied to VQA, where the task is given an image and a free-form question like, what is the person hitting? The model has to produce an answer. Using GradCam, in this case, we find that the model looks at the ball and uses a little bit of the context to answer tennis ball. So we see that even simple non-attention-based CNN LSTM models look at appropriate regions. And then another thing that we found is that even unreasonable predictions sometimes have reasonable explanations. For example, here for this particular image, the model predicted it to be a car mirror, and you can see that seeing the visualization, it somewhat looks like a car mirror, right? But the ground truth category was actually volcano. And of course, if you ask where should the model look to predict volcano, it will look right at the middle here. Similarly, this is an example where the model predicted wine snake. The ground truth was actually coil. For the wine snake visualization, you can see that it actually looks somewhat like a wine snake. But when trying to visualize the ground truth category coil, it looks at the whole of the coil. So even unreasonable predictions have reasonable explanations. I will quickly show a demo I'll fast forward a bit.
And while Ram is pulling up the demo, I just want to comment that we will get to RNNs and LSTMs later in this class. And so we will teach you how to do image classification and VQA models. Don't worry about it. It's coming in the next module. Back to you, Ram.
Yeah, you're able to see my YouTube running, right? Or is it not?
It is running. I can see it.
Okay. Okay. So here, for the example, what color is a fire hydrant? We are like visualizing different kinds of answers and seeing what the model actually thinks. And here, for example, this is a captioning example. We are now asking the model to predict a caption. It says a large house with a large stone wall, and you can see that it actually looks somewhat at the somewhat some stone wall kind of thing. But here you can see that there is a horse in the image, but it does not talk about the horse. So let's see if it can visualize the horse. So it is able to visualize. Now let's change the caption to maybe say a horse standing next to a large house with a large stone wall. And now the model seems to look at the horse and a little bit of the stone wall. And here's a classification example for a zebra. It looks right here. Now change the category to hippopotamus, and then it looks at these regions. So yeah. Now we looked at where which pixels affects the decisions from models, but now can we see if humans, if CNN and Samvad are looking at similar regions to humans? Yeah, so this was work done by Abhishek Das and Harsh Agarwal, again from our lab. Here, what they did was they collected human attention maps from humans. So for that, what they did was to blur the image of interest, and people were given a question: how many players are visible in the image? So the task for humans was to de-blur some of the regions where they might think has players, and then answer the question. So that way you get a visualization like this. So here are a few more examples of what food is on the table: cake, what animal is she riding, or what number of cats are laying in the bed, and so on. So now you can ask the question, like, are GradCam explanations somewhat human-like? So what we find is that compared to other approaches, GradCam explanation seems to indicate that current models somewhat look at the same regions as humans do. But in future work, we also found that like this does not happen often, and we looked at ways to provide supervision to make sure that GradCam actually looks at the same regions as humans do and see how the model performance changes. Yeah, coming to the last part, here we're asking the question, how can we synthesize images to see what the networks are actually looking for? So this is a question that eventually led to this whole new field of adversarial machine learning. We'll get to that in a bit. So the first question is, can we get an image that is representative of a class? So we're basically performing gradient ascent on pixels. So we're asking what type of input in general would cause output neuron to activate. We can answer this question by a technique called gradient ascent. So we always use gradient descent to train our convolutional network by minimizing the loss. Instead, we want to fix the weight of the convolutional convolution network. And instead perform gradient ascent on the input image to see and try to find images that maximize the score for some intermediate neuron or some particular class that we care about. One thing that people have found is that like directly doing gradient ascent does not work. It leads to random noisy images that might not be very meaningful to look at. So people found that they had to add these kind of regularization terms to prevent the network weights from overfitting to the training data. Like for example, regularization terms have been used during network training to prevent overfitting. Here, the use of regularization is to generate an image which is natural looking. Yeah. For example, what we do here is we start with some initial image. We either initialize it to zeros or uniform or some kind of noise, and we then forward the image through the network and compute the score for the class that we are interested. Now we backpropagate to compute the gradient of that neuron score with respect to the individual pixels in the input image. And then do small gradient ascent updates to the pixels of the images itself. And then we repeat this process over and over again until some kind of a convergence. For example, this is what.
Ram, can you go back a slide? I just wanted to. Can you go back one slide? Yeah, thank you. Yeah, this is perfect. No, actually, the one right after this was perfect. So I just wanted to make a quick comment that this is, as Ram mentioned, very different from what you're used to in the class, right? We're used to the parameters in the CNN being the optimization variable and the data or the data set, the image and the labels being the fixed quantities, because that's usually what is fixed. You do not get to change your training data set. This is a very mathematically elegant but also somewhat liberating way of thinking about this, that your data can also be a quantity that you can optimize over, and you can optimize with arbitrary objectives, because as long as you can write down a differentiable loss, typically the architectures are treating data and parameters interchangeably, and so what's differentiable in W is also differentiable in I. And therefore, backprop is doing most of the heavy lifting anyway. Reverse mode automatic differentiation is getting you to the leaf nodes of the DAG, and the leaf nodes of the DAG for us are both the input pixels and the parameters. And so we're almost there. Running backprop one extra layer gets us the gradients, and because we're doing gradient descent, we can do optimization of these objectives. It's a very different way of thinking about it, and I want you to keep this in mind as you approach different problems. Can I optimize over my data? Go ahead, Ram.
Yeah, here we use regular L2 regularization, and for the class dumbbell, you can see that the model, like when you do this procedure, it somewhat generates some dumbbell-looking structures here. And here, see for Dalmatian, you have a black and white blobs here, and bell pepper is more clearly visible here, and so on. There have been a lot of different kinds of regularizations that people have tried to improve the kind of images that are generated. Here, actually, I did not add a link to the particular blog. There is an interesting, when I upload the slides, I'll add a link to that blog that explores all these kind of different regularizations. Yeah. So now, can neural networks be fooled, right? For example, what we can do is say pick some particular, say, arbitrary image. It could be a zero image. We can and then pick some arbitrary class, and then we can modify the image to maximize the probability for a class, for some arbitrary class. Repeat this until the network is full. Very simple. I'll explain again what we are doing. Here, we take the image of an African elephant that we saw before. Let's, take the class koala, and then one hot encode koala. So basically 0, 0, 1 at the location of koala, and backpropagate all the way to the image, just like we did earlier. And we update the image, and then you do this enough times, so the prediction actually changes from an African elephant to a koala. But here you can see that the difference is like very minute, but the network seems to have completely, changed its prediction to say that this is a koala. And even a 10x difference of that, like is not very meaningful here. So these again here, you can convert this image to, like, say, an iPod. Again, these networks are very easy to be fooled, and this has led to a lot of research and adversarial machine learning, and this is clearly problematic, right? Like imagine autonomous driving car. You can actually fool. You can place some kind of stickers on, say, stop signs that will make them think that it's a 65 miles per hour highway, right? So the car is not going to stop for stop in the stop sign, and it's going to cause problems, right? So so these things can happen, and we as researchers have to, think about how we can, fix these networks and so on. This many people might have heard. This came up in, I think, 2015 or 16 by Google, called Deep Dream. Another cool thing that we can do with this gradient-based optimization of images. So this was a blog post from Google. So essentially, what we're doing is we're choosing an image and a layer in a CNN. So what we're doing is we are computing the activations for any chosen layer, and then set the gradient of the chosen layer to be equal to its activation. So I'll describe why we are doing that. And once you compute the gradient on the image, you update the image and then keep repeating this process. So the reason you set the gradient of the chosen layer to equal its activation, so essentially what we are trying to do is, if the network is, say, detecting something, make it detect more of that. So how would you have to change the input image to make the network detect more of what you're detecting at that particular layer? That's exactly what we are doing. So for example, here, this is an image, just a regular sky image. Like when you repeat this process, like at some particular layer, you get a lot of these castle looking structures, castle combined with some kind of other animals. Like, why do we see things like this, right? So if you see a bunch of these Disney castles, like their background is actually a sky, right? So just by seeing, so model somewhat has learned this correlation between sky and castle. So because it sees a sky, it thinks that there is a castle somewhere, and it might be producing a very small activation for castle. And now that I'm asking the network to now I'm changing the image so the network detects more of the castle. It updates it more and more, and finally we are able to see some castle looking images. And people have actually found different kind of interesting visualizations here, and these have some names also: admiral dog, a pig, snail, camel, bird, dogfish, and so on. Yeah. So then the next question. So given the
Actually,
feature vector,
Ram,
yeah,
can I just make a quick comment? So that
yeah.
last thing, now I just want to comment that these sorts of visualizations are now firmly in the realm of creativity. That you could argue that we were creating saliency visualizations to try and understand which pixels are important or sensitive, what are categories sensitive to. You can say that, prototypical images that Ram talked about, maximizing, so what sort of images maximize the score for a particular category, tell you something about what the network has learned to look for, what it considers a prototypical image. Maximizing the activation at a particular layer, setting the objective function to be the norm of the activation at a particular layer. Now these are firmly in the realm of creativity. It is unclear if this really gives you any insight about what the network is doing. Go ahead, Ram.
Yep. The last question here. Given a feature vector, can we reconstruct the image that'll give that'll maximize that feature vector? For example, this is an area called feature inversion. So we're basically using the same tools that we have used before, just to see what information the network retains and what information is lost and so on. This again gives us a sense of what type of elements of the input image are captured at different layers of the network. So what we're going to do now is we're going to take an image, run that image through the network, record the feature value of, say, one of the layers, and like we are going to try and reconstruct that image from just the feature representation. So the question now, based on how much and like what kind of reconstructed image looks like, we can get a sense of what information is actually retained in that particular layer. Yeah, so let's and again here, people have found that this is the original feature vector, and this is the feature of the new image, and we are minimizing the distance between this reconstructed feature and reconstructed feature for this new image X to be closer to that of the given feature vector. And people have found that you need to add a regularization term here to make these images look somewhat meaningful. Here, one of the popular regularization that people use is a total variation regularizer that encourages the pixels around the pixel of interest to be somewhat smooth. Here is a visualization here on the top below. We can see that's the input image Y. Here is how, if you take the con2 layer of a VGG16, this is basically after the value. If you try to reconstruct the image using the subjective, you get a very similar looking image. As in when you move away from the input layer, you can see that like you're not able to reconstruct it as clearly as you can, right? That's mainly because of the kind of invariances the network has learned. So the information is getting lost when it goes through all these layers, and that's why we are not able to reconstruct these images very crisply. Yeah, so that brings us to the end. So today we covered, how individual neurons, like what do individual neurons look for in images, what pixels affects the decision the most, and we saw if humans, like networks look at the same regions as humans do, and we looked at this line of work where people synthesize images to understand more about the network. And yeah, thank you so much. And one last note here, Salesforce Research is looking for interns. So if you're a PhD student who's interested in exploring the intersection of explainable AI and representation learning, please consider shooting me an email. My email address is right here. Thank you so much, Dhruv, for the opportunity today. And thanks everyone for attending.
Great. Thank you, Ram. So we are done with introducing new content. And Ram, what we usually do is that we let people leave at this point if they want to. But if they want to just hang around and ask more questions, I am usually answering those questions at the end of the lecture. And I imagine, do you have a few minutes to answer questions if they come up?
Yeah, I do.
Okay. So yeah, if people want to leave, you're welcome to head out. But if you want to ask any more questions to Ram or anything that we have covered in the lecture today for me or how this fits in, we're happy to stick around and answer those. You can paste them in the Q&A tool.